To state the central limit theorem formally, let's begin by looking at the sequence xn bar minus mu. I have subtracted the expected value, so this will be a sequence of random variables. The expected value of each one of them will be 0 because this one has expected value mu. The variance of this sequence will be the same as that of xn bar, sigma square over n, since mu is a constant. So that will be the first step. In the second step, let's look at the sequence square root of n times xn bar minus mu. So basically, I'm starting with this sequence, and as n increases, I multiply by square root of n. So I'm multiplying by a bigger and bigger number as n increases. The expected value of this sequence, square root of n x bar minus mu, that would be square root of n times 0, so it's still 0, while the variance of this sequence, we can take the square root of n outside, we have to square it, so it becomes n times sigma square over n, so it becomes constant sigma square. That's the important part. If we look at this sequence, it's a sequence of random variables where the variance gets smaller and smaller and smaller because we divide by n. If we look at this blown up sequence where we pre-multiply by square root of n, we will actually have a sequence of random variables where the variance stays constant. The central limit theorem tells us that if I look at this sequence of random variables, xn bar minus mu, then this sequence of random variables will converge in distribution to any random variable which has a normal distribution. So we typically just write the name of the distribution with the expected value 0 and with variance sigma square. So note that for this sequence, the expected value is always 0 no matter what n is. The variance is always sigma square no matter what n is, but the distribution is not in general normal for a given n, but it converges to a normal distribution. The PDF of this random variable will become more and more similar to the PDF of a normal distribution with expected value 0 and variance sigma square. So this is the central limit theorem with the conditions that we have used in this lecture, that I have a random sample. Then this particular central limit theorem goes by the name Lindberg-Levy central limit theorem. There are many versions of the central limit theorem, and they differ in the assumptions that are made. Sometimes you see the central limit theorem as square root of n xn bar minus mu over sigma. This is the same sequence of random variables as the one we've been looking at, just multiplied by 1 over sigma. Since the denominator converges to a normal distribution, and we know that a constant times a random variable that follows a normal distribution will itself be normal, we can conclude that this too will converge in distribution to a normal. The expected value will be the expected value of this one. And since the expected value of the numerator is 0, this will have expected value 0. The variance will be the variance of this one. And the variance of this one is the variance of the numerator divided by sigma square. So it will be sigma square over sigma square, so it will be 1. The sequence to the left converges to a standard normal. So what we can say is the following. If n is large in the sense that the distribution of this part is now very close to a normal. Exactly how large n needs to be, well, that depends on the distribution of the xi's. But if it's large enough, it will always happen eventually. In that case, we can write that square root of n xn bar minus mu is approximately normal 0 sigma square. It's not going to be exactly normal, but approximately. And the bigger the n, the better is this approximation. So let's say that x is a random variable with this exact distribution, normal, 0, sigma square. Then by dividing both sides by square root of n, we have that x(n) bar minus mu is x over square root of n. The right hand side is simply a constant times the normal, so we know that this will still be normal. The expected value will be the expected value of this, and since x has expected value 0, as you can see here, x by square root of n will have expected value 0. The variance of x over square root of n, take that outside, it's 1 over n times the variance of x, and the variance of x is sigma square, so this will be sigma square over n. If we just add mu to both sides, we see that the sample mean is approximately distributed as normal mu sigma square over n, and this is the important result that we use from the central limit theorem. Even though I have no clue what the distribution of the sample mean is, if n is fairly large, I know that it's approximately normal. We will look at some simulations in the next lecture to see that in most cases this approximation goes pretty quickly. In some cases the approximation is almost perfect, even with n equal to 5 or 6, and some cases you need to go higher to like 20 or 30. An important point to make once we have realized that we can approximate the distribution of the sample mean is to point out that the sample mean itself does not converge in distribution to a normal. This is a very common mistake. I guess the simplest way to realize that this cannot happen is to look at this approximation. When n goes to infinity, sigma square over n will go to 0. And this is a result that we've talked about before. Actually, xn will converge, but not to a normal distribution. It will converge to a constant, and the constant it converges to is the number mu. This convergence will happen in probability. That's what we call the law of large numbers, and it will also happen in distribution. It's very important to remember that there is no convergence of the sample mean to a normal. In the central limit theorem, we absolutely need this square root of n factor for convergence in distribution to happen to a normal. Basically, what's happening is the following. This parenthesis here tends to converge to a constant. The distribution of xn minus mu will eventually become a spike around 0. This term here, square root of n, will counter that effect. Square root of n will become bigger and bigger as n increases, while the second term will become closer and closer to 0, and these two terms will balance each other out exactly to create a nice distribution. A distribution that will not collapse to a spike and a distribution that will not explode. So here is an example of what I mean by this common misconception that the sample mean converges in distribution to a normal.
What's cool is we can start with some crazy distribution. Right? This has nothing to do with a normal distribution. But if we have a sample size, this was n equals 4, but if we have a sample size of n equals 10 or n equals 100, and we were to take 100 of these instead of 4 here and average them and then plot that average, the frequency of it, then we do take 100 again, average them, take the mean, plot that again. And if we were to do that a bunch of times, in fact, if we were to do that an infinite time, we would find that especially if we had an infinite sample size, we would find a perfect normal distribution.
I don't bring up this example to be critical against Kohn, but it is important to point out that the sample mean will in no way converge to a perfect normal distribution. That would be completely contradictory to the law of large numbers. Kohn also points out that the central limit theorem applies to sums, and this is true, but we need to replace this factor here.
That's the crazy thing. And it doesn't apply just to taking the sample mean. Here we took the sample mean every time, but you could have also taken the sample sum. The central limit theorem would have still applied.
So by the central limit theorem, square root of n xn bar minus mu converges in distribution to normal 0 sigma square. I can replace the sample mean with its formula. It's a square root of n 1 over n summation xi minus mu, and this is equal to 1 over square root of n summation xi minus square root of n times mu. This will converge in distribution to a normal 0 sigma square. But again, it does not mean that the sum converges in distribution to a normal. Think of a simple case where the range of each xi is, say, from 0 to 1, then this is a sum that goes from 1 to n, and if you let n go to infinity, this will clearly converge to infinity, not to a normal. It will only converge to a normal if we subtract this and pre-multiply the sum by 1 over square root of n. Then it will converge to a normal.